How about now? Better? Any better now? That's the maximum the mic can go. So. Okay, thanks so much everyone for coming. It's a real pleasure to get a chance to talk to you. Despite the number of people that are turned out, apparently there's no one to actually introduce me, so I'll introduce myself. So I'm Brendon Bradley. I'm an academic here at the University of Canterbury, obviously. I work in the civil and natural resources engineering department. And I'm also the Deputy Director of Quake Corps, which I'll talk a little bit about toward the end of the presentation. It's the New Zealand Centre for Earthquake Resilience. So I'll just jump straight into it. The title of the talk, obviously, as you can see there, is What Will an Alpine Fault Feel Like? Relatively simple title, obviously, very engaging given the audience, but also extremely vague, okay? Because if you've all had pretty good experiences with earthquakes, presumably, and you know that, for example, what will an Alpine fault feel like is going to depend on where we are, okay? And we'll talk a lot about some of the details here on how the location we might be matters. But just so I can understand a little bit more about you, how many people are not from Christchurch? Okay, I assume you all reside in Christchurch, although you don't identify as Canterburyans. Okay. How many people live to the west of Hagley Park? About half. And to the east of Hagley Park? Okay, excellent. Good, okay, it's good to know the audience. So, obviously I can give you some insights into this question of what an Alpine fault earthquake might feel like. I can tell you to kind of just trust me, I know what I'm talking about, but most of you won't. Okay? And the reason for that is obviously you can't just trust someone. You have to actually really understand and have some appreciation for what they're saying. And so rather than me just simply try and answer this question directly, what I'm going to try and do is take you through a bit of a journey that I've been on in the last sort of 5 years as we've been trying to understand the outcomes of the Canterbury earthquakes. And then hopefully as we address the title of the talk towards the end, you have an appreciation for some of the subtle aspects, things that are important, things that are less important, and then you actually go away from this talk and you act as champions to teach the other 400,000 people that aren't in the room in Christchurch, the other 4 million people in New Zealand, why some of the things that we're talking about here tonight are important. Okay, so we're going to go through several different sections as we kind of go through the talk. Just bear with me for a second. Perfect. Okay. So firstly, some context. So I understand, most people are here from Christchurch, and so why is this important? Well, obviously, 5 years ago we've had the start of the Canterbury earthquake sequence. It's been relatively quiet over the last few years. Of course, the earthquake on the 14th of February this year gave us a reminder that that sequence is not over. We can expect to have a few more earthquakes than what we used to have prior to 2010. But we understand really well, either we've observed it directly or many people have told us the impacts of those Canterbury earthquakes. Okay? But we're much more interested in what happens in the future. Will the observations that we've made in Canterbury occur again in Canterbury in the future, maybe from some other earthquake? Will they occur somewhere else in New Zealand? And what about even other locations around the world? The example shown here is San Francisco. In order to really understand this question, we have to sort of separate the physical effects that we've seen from the Canterbury earthquakes in the last few years, and the two key distinctions that we have to make are shown here on the slide. The first one is we have to be able to understand the demand of the earthquake. How strong was the ground shaking that excited all the different things and caused the damage? And then secondly, the vulnerability of both the natural environment and the built environment. It's the combination of those two factors that's going to determine how much damage a particular earthquake causes. Okay? So the focus of this lecture is really on the first one, understanding how earthquakes cause ground shaking and how the different features of New Zealand, the different features of earthquakes can influence that ground shaking. But I'll touch very briefly on the second point in terms of vulnerability for the last few slides. So why is this important? Well, of course, we've got New Zealand's South Island here. I'll restrict this talk to really focusing on the South Island, and that's for two main reasons. One, because of lack of time, and two, because of the location where we are today. But don't think for the minute that this implies that the South Island is either good or bad, and that the same things won't happen in the North Island. Okay? So it's simply for context and for lack of time. The Alpine fault, okay? The question, the title of the lecture is what we call the plate boundary fault. It's the fault that divides the Australian plate on the upper left from the Pacific plate on the lower right. However, while it's really useful for us to talk about the Alpine fault, there are many more faults in New Zealand. Okay? If I gave you, as the title of this lecture, some small fault you've never heard of, chances are the audience would be about 1/10 as much as it is now. Okay? So using the word Alpine fault is particularly good. It allows us to have a common understanding of what we're talking about, but the Alpine fault is not the only important fault in New Zealand. This is a map of the mapped faults that exist in the South Island. It was compiled at the end of 2010. It's sort of a national consensus model, and it represents the key large potential earthquakes in the South Island. Okay? They are mapped faults. They are not every fault. You'll note here that there aren't the faults which ruptured during the Canterbury earthquakes. And you'll also note in general that actually as we move away from the Alpine region and we move into the sedimentary areas, the soft soils here in Southland and Canterbury and some areas into the west coast, our mapping of these faults is less dense. Okay? That's not to suggest that we didn't know that there were faults there, it's just our conventional way of understanding where faults are isn't as easy to do when we have soft soils over the top of the rock. So again, we've got the Alpine fault, but there are these other faults which are important. Okay, so let's start by trying to understand, maybe from a little bit of a scientific point of view, all the experiences that many of you have had based on your being here during the Canterbury earthquakes. So it all started for many of us around this time, 4:35 a.m. on the 4th of September 2010. Okay? Many of you will sort of draw back to, were you sleeping at the time? Presumably most of you. And what were your initial impressions once you were suddenly woken up? Okay, so the thing that you felt from your own perspective, from a technical perspective, looks something like this. Okay? And what this image is showing is the ground velocity, think of it as the strength of the earthquake shaking, moving in the north and south direction as a function of time. Okay? So the reason that we understand this is because throughout New Zealand we have a relatively dense array of instruments that record that ground shaking. So on this map here we've got the same topography we had before, and each one of these triangles there is located what we call a strong motion instrument. Okay? So these yellow boxes, this is one type of strong motion instrument, there are others, they record the ground shaking when a particular earthquake occurs. And this is really the main way that we understand the phenomena of earthquakes and all the characteristics of those earthquakes as well. So each one of these little yellow boxes is able to record the ground shaking in three components, okay? Because many of you will be well aware that an earthquake causes ground shaking in three different directions, so it can record two horizontal directions of shaking and also the vertical direction of shaking as well. By making use of these strong motion instruments located over the Canterbury region, this is an example of the type of information that we were able to observe from a technical perspective in the 4th of September 2010 Darfield earthquake. Okay. Just to highlight on this figure, the red parts here represent fault, the actual two sides of the earth that ruptured and moved and caused the ground shaking. And then at every single different location you can see here was the ground motion that was recorded at that location. If you look relatively closely, you can see that every record at every different location is relatively unique, and much the same as you, there's no two records that are exactly the same. Okay? Every earthquake recorded at every different location will give us some slight differences in the response that we see. However, the important things are, despite this apparent complexity, there are some general features that we can understand, and it's our ability to understand those general features that enables us to better predict the ground shaking that earthquakes can cause. Same sort of idea now, but looking at an image for the 22nd of February 2011 Christchurch earthquake. Again, the red square approximates the area, the two sides of the fault which actually ruptured. And many of you will be aware, of course, that because of the proximity of that earthquake, you can see here it's under the southern part of Christchurch, that tended to result in stronger ground shaking and consequently the much greater damage that we observed throughout the city. But of course, the Canterbury earthquake sequence wasn't just two earthquakes. We generally think of them as the four main earthquakes, so I've got the two previous ones shown on the top left and top right panels, but also the other two important events, 13th of June 2011 and 23rd of December 2011. Okay? These were the four main earthquakes that really caused probably something like 99% of the total amount of damage. Okay? And while the other earthquakes are a constant disruption to our everyday lives, their contribution to the total damage as a result of the Canterbury earthquake sequence really hasn't been that significant. So the important thing from this sequence is the incredible scientific data that we've been able to collect. So you imagine that from these earthquakes, which occur very infrequently, we've managed to have these density of instruments to record all the unique features associated with each different earthquake. And then because, of course, the earthquakes have, unfortunately for us, happened in the same region consistently, we've actually been able to observe at the same set of locations the ground motion earthquake after earthquake after earthquake. And so it's this great data set that is one of the positive outcomes from the sequence and is allowing us to improve our understanding of earthquake shaking, and hopefully that's going to lead to significantly better outcomes in the future, which I'll try and talk about. So before I get into some of the more complicated aspects of ground shaking, and when I say complicated, I'll manage to keep away from the complications, but be aware that there are some. Let's just start with some very simple aspects of ground shaking. And when we talk about simple models, we often refer to these as empirical models. So just a quick rapid fire questions from the audience. When you think about earthquakes, what are the things that you think matter?
Noise.
The noise, okay. What about in terms of if you're worried about how strong the shaking is going to be, what do you think are the main factors that influence the strong shaking?
The security of building.
No, so the aspects of the ground, the building, the depth. Distance? Magnitude. Okay, anything else?
The ground you're on.
The ground you're on, and what do you mean by that?
The density of it, the textures of it.
Yep, so why the eastern suburbs were so much worse affected than the western suburbs? Okay, so we can think about this empirical estimation of shaking really in terms of three things. What we refer to as a source effect, a path effect, and a side effect. Okay, so if I use this very simple schematic, when we talk about a source effect, we're really talking about the magnitude of the earthquake. Okay? You're all experts in earthquakes in Christchurch, so you all know what I mean when I talk about the difference between a magnitude 4 and a magnitude 5. Okay? When we talk about a path effect, we're referring to the distance. Okay? Because remember, the important thing is the magnitude of the earthquake tells us how much energy is released at the fault. Okay? It's not a property of the ground shaking. As you'll know, that as you get further and further away from where the earthquake location was, that actually the strength of the shaking gets weaker and weaker. Okay, so that's what we refer to when we talk about this path effect as a function of distance. And then finally, the comment here was mentioned what we call the side effect, depending on whether you're on rock or soil. For example, here's a schematic of some soft soils and the increased damage that happens. And then also, importantly, you can have side effects associated with being on hills or other important topography. Okay, the other aspect that we do is we take this complicated record of how the ground accelerates as a function of time, and we simplify. Okay, one of the easiest simplifications that we can do is take the maximum value, or the peak ground acceleration. Okay, to draw an analogy here between the weather, rather than understanding how the weather fluctuates for every minute of every hour in the day, we tend to summarise the weather by the maximum temperature, the minimum temperature, and how many millimetres of rain we have. Okay, so we use these very simple indices to describe the shape, to describe the weather. In the same way, we take this complicated acceleration as a function of time, and we describe via some simple intensity measures the intensity of that shape. Okay, so this is the single most complicated slide as part of this presentation, so bear with me for one aspect here. And this is our previous measure here, peak ground acceleration. And as you know, it varies as a function of distance. The further away we get from the earthquake, the weaker the shaking. And the two figures on this plot, each of the different points represent one record from one of those instruments. Okay? The figure on the left-hand side is for the 4th of September 2010 earthquake, and the figure on the right-hand side is from the 22nd of February 2011 earthquake. And what you can see by and large is that all of the dots, which are all of the recordings from these instruments, are relatively consistent with the solid black line. Okay? And this solid black line is one of our empirical models that we would use to predict what the ground shaking would have been from each of these different earthquakes. Okay? So you can see that our empirical models are pretty simple. They're just essentially a curved line where the amplitude reduces as we get further away in distance. Okay? And the other important thing to understand here is whenever you're dealing with something complicated, use a log scale. Okay? So we've got here on the y-axis a log scale, which makes very scattered data actually look relatively closer together. Okay? And so one of the things that we can just use is if we look at these two dashed black lines, they represent a factor of about 2.5 times difference. Okay? So the shaking corresponding to the lower black line and the shaking corresponding to the upper black line is about a factor of 2.5 different. Okay? So while we can see that these empirical models on average do a relatively good job and are consistent with the observations, we can see that there's a significant amount of scatter in the observations themselves, and so that's not particularly useful from that perspective. More importantly, you'd expect that as we better understand earthquakes, as we observe them over time, as our models start to get a little bit better, you'd expect that this uncertainty in the predictions would reduce. So this figure is plotting prediction uncertainty here on the y-axis versus the publication year of different models on the x-axis. Okay? So you can see that the field of prediction of ground shaking started sometime in the early 1970s, so it's about a 40-year-old profession, shall we say. But the important thing you can see by looking at all of these different models, okay, so different models for different parts around the world, because not every place is exactly the same, that really we have sort of an average trend which is pretty much a flat line. Okay? So we're not really getting any reduction in our ability to predict the shaking using these simple empirical models. Okay? In order to understand why, let's come back again and look at this analogy of the weather. Okay? We're, again, like being experts at understanding earthquakes here in Canterbury, New Zealand, are experts at understanding the weather. Okay, so our empirical model for the weather looks something like this. The month of May, we have the full months in days there on the x-axis. We have our average historical high in the solid red line, our average historical low in the blue line, and then we also have some uncertainty around those values. You know, our historical on average is the solid red line, but we also have some variation. So if we were to use this empirical prediction for the weather, we'd basically say, well, okay, tomorrow is the 25th of May, so we'd come in here just after that value of the 21st, and we'd say the weather forecast for tomorrow is going to be a high of 13 and a low of about 3.5. Right? Sounds ridiculous to suggest that that's how we predict the weather, doesn't it? Okay? The reason for that, of course, we know, is that these are averages, but actually we can have significant deviations from these averages. And so we use, in our weather forecasting as part of everyday life, a physics-based model. Okay? And so we understand, you know, highs and lows and tropical cyclones and so on and so forth, and it's our understanding of the physics that enables our weather forecasting to be significantly better than our empirical models. Okay? And it's not that the empirical models are wrong. You know, by definition, this empirical model is based on historical data, so on average it's correct. It's just that it doesn't have much precision. Year to year, the weather on the 25th of May is going to be quite different. The second thing is that it's not that meteorologists predicting the weather are fundamentally smarter than seismologists predicting earthquake shaking. Okay? And our ability to predict things well depends on three key factors. Okay? The first factor is that we can actually observe the phenomenon. Okay? Understanding the weather is much easier than understanding earthquake ground shaking because the weather is above us and the earthquake-induced ground shaking is below us. The second factor that's important is the frequency at which we observe the data. So one thing, if you think a little bit more carefully about weather prediction, our weather forecasters can predict average weather particularly well, and they can't predict storms very well. Okay? They can't predict threshold events very well, whether it rains or it doesn't rain. Okay? You'll often see on the Met Service 0.1 millimetres of rain, and you'll notice many times it doesn't rain. Okay? So it's quite hard for us to distinguish between those two different aspects. And then the third thing that's important is the local scale. Okay? In weather terms, we call this a microclimate, the tendency for the weather to vary quite a lot over small distances. So this is another thing which is particularly important as well. Okay, so now that we have a bit of an understanding of the limitations of these empirical models, why physical models work well in the case of weather forecasting, let's now think about physics-based estimation of ground shaking for earthquakes. Okay, and the same three factors that I just mentioned for weather also apply for earthquakes. And so can we significantly improve our ability to predict earthquake shaking by using a physics-based approach? And the key aspect here is that it's not the difficulty in actually doing the prediction. Okay, what I've got up there in that first bullet point is that actually numerically predicting earthquake shaking is relatively easy, but it's difficult to produce predictions which are actually accurate. Okay? And there's three key factors for that, and again, they relate to these same three important terms that I mentioned before: the earthquake source, the path, and the side effect. And the reason why we've been able to make significant progress in using these physics-based methods is because of the fact that we've had rapid growth in high-performance computing. Okay? Our computational abilities have enabled us to solve problems that before were just not possible. As we've been able to consider things more completely and more complexly, we've significantly improved our prediction. Okay, so let me just go back to here. A quick question again for all of you. This is a question as, how long does it take for an earthquake to occur? Okay, and we've got three different choices. One is less than 3 seconds. 2 is between 3 seconds and 10 seconds. And the third is longer than 10 seconds. Okay, so who's up for 1? Less than 3 seconds for an earthquake to occur. Okay, a few hands. Between 3 and 10 seconds. And more than 10 seconds. Okay, and who chose not to answer? Okay, so you're all right and you're all wrong at the same time, okay? And the reason for that is it depends, okay? And the reason it depends is because it depends on the magnitude of the earthquake, okay? Because an earthquake doesn't just occur, okay? One of the most interesting things about thinking of earthquakes is that the difference between a magnitude 1 earthquake and a magnitude 8 earthquake isn't actually clear when the fault first breaks. It's what happens after the first bit of the fault that breaks, which determines if it's going to stop and it's just a magnitude 1, or whether it carries on and sort of cascades out of control and causes something actually not a magnitude 8, but something even bigger, like a magnitude 9. Okay? So this is an example to try and illustrate some of the complex aspects of an earthquake fault, and we're going to use an example from the magnitude 9 earthquake in Tohoku in Japan, March the 11th, 2011. My wife and I happened to be in Japan at the time, and let me just see the video from the start. This initial star represents the location where the earthquake commences. And what we're going to see is an animation in time. The left-hand side is illustrating the instantaneous movement, and the right-hand side is the cumulative movement. So what you see is it starts at a single point, but then it propagates outwards in the same way that, for example, you knock over dominoes. You knock over the first domino, and then subsequently each of these different dominoes cascade, and they cause eruption. Okay? And so the important thing to understand is that an earthquake isn't just suddenly happening, that it starts by two sides of the fault moving, and over time it starts to cascade out of control, and eventually it'll get to a point where the increased stress beside the point of the fault that moved isn't enough to cause the next point to break. Okay? And that's when the rupture, what we call, arrests, and the earthquake itself stops. Okay, so that's associated with the source. Okay? The next aspect that we talked about before was the path, how far away we are in terms of distance. But it's important to understand that not all distances are equal. And what I mean by that is, if we look at this image on the screen, we've got a sort of a cross-sectional diagram of the Canterbury region. So you can see here in the plot in the bottom right-hand corner, the Canterbury Basin. And then each of these different red lines here represent different points on that cross-section. Okay, so for example, here is, you can see Banks Peninsula. Here you can see the Southern Alps, the foothills, and then the Alps itself. And on this line here, we're down somewhere near Rakai. Okay? And the different colours on that diagram represent the stiffness of the soil. Okay? So warm colours, the red colours are rock, and the lighter or softer colours in blue are our sedimentary soils. And what you can see as you look across each of those different transects is that the thickness of the soils in the Canterbury region varies quite significantly depending on where you are. Okay, so under Banks Peninsula, of course, we've got the volcanic rock, so you have rock immediately at the surface. And then as we move away from, here's the Port Hills, we eventually get into Canterbury itself, and as we move north from Canterbury, the thickness of that basin increases. And when we're out in other areas, for example, up here in the Ashley region, we go from the rock immediately into soil, which is particularly deep. Okay? And the important thing about this is how this distinction between soil and rock changes the way that when an earthquake occurs, the ground shaking moves around the earth. Okay, in order to understand this, let's quickly deviate and talk about refraction and total internal reflection. And the example that we can use here is simply looking at light, because light also is partly a wave. That when we have this light beam coming in from the left-hand side of the diagram, we have the incident wave associated with the light, and then when it hits this plastic arc, we get two things. The first is that we have a reflected wave, a wave that is bent backwards in the opposite direction, and then we have a transmitted wave, which goes through the interface, or that boundary, and carries on. And then in this particular case, because of the shape of this plastic arc, that transmitted wave eventually hits another interface, and again, that interface, we have an incident wave, a reflected wave, and a transmitted wave. So one terminology that we refer to as the difference in direction of this incident wave and the transmitted wave is what we call refraction. Okay, it's the same thing when you're in the bath, you've got your hand under the water and you look at your arm and it looks big. Okay, it's the same phenomenon. The important thing is that this amount of refraction depends on this incidence angle, okay, the difference between the red line and the black line. So if we take the same example on the left-hand side and we now look at a similar example on the right-hand side, but the only difference now is that we've slightly rotated that plastic arc such that now the slope of it is slightly flatter relative to the previous slope. Now what we see is that that incident wave is completely reflected, okay, and there's nothing transmitted out the right-hand side of the diagram. Okay, so this process, or this phenomena, when we have the incident wave completely reflected, as would be logical for a name, is total internal reflection. And the important thing about this is that it means all of the energy is trapped within the medium that it was currently in. Okay, so think of it as nothing was able to escape from that aspect of the plastic arc. The importance of this phenomena is that when we talk about seismic problems, so when we have earthquake and we have the ground shaking, think of this plastic arc as the soil and think of the air beyond it as the rock. That when these waves in the soil hit the rock boundary, if they hit the rock boundary at a good enough angle, actually they're completely reflected back into the soil rather than escaping into the rock into the distance. Okay? And in some of the images that I'm going to show you soon, you'll see this phenomena where we have total internal reflection results in ground shaking, which lasts a lot longer than it does elsewhere. The other thing, I mentioned three things: source effects, side effects, and path effects. Okay, so as I've just alluded to, in Canterbury we do have these deep sedimentary basins, and so in order to be able to better understand the basin, we've conducted a lot of soil testing. So each of the different red or blue points on this diagram represent areas where we've gone and we've tried to characterise the soil. We've used a range of different techniques to do this, from as simple as the little blue boxes here, which just record the ambient noise. The noise, when we say noise, we mean vibrations due to wave action, due to the wind blowing the trees, and the trees actually cause the ground to vibrate a little bit. Or we use what we call active methods, where we actually apply the vibration to the ground. So we can do this using a sledgehammer, for example. We can even do this using large vibration machines. Some of you may recall about 2.5 years ago when we bought this machine called T-Rex from the University of Texas, Austin, here to Christchurch in order to undertake some of this testing. And just to give you an example of the importance of this source, path and side effect, let's look quickly at Heathcote Valley. So Heathcote Valley, for most of you will know, is at the southern end of Christchurch, right at the boundary as we go under the Port Hills through the Littleton Tunnel to Littleton. And this top diagram is basically indicating the depth of the soil. Okay? As you'd expect, you come up towards the head of the valley, the depth of the soil decreases. And then imagine that I'm taking a horizontal slice through that diagram. I get a picture that looks something like that at the bottom of the slide. And the important thing is that in Heathcote Valley, this was the location which consistently, one of the instruments was recording the strongest ground shaking, earthquake after earthquake after earthquake. Okay, in the February earthquake, for example, the horizontal ground shaking was 1.4 G. Remember, G is the acceleration of gravity. And in the vertical direction, it was 2.2 G, twice the acceleration of gravity. Okay? These were consistently the highest levels of acceleration seen at this one location. And the reason for this, I'll show you here in animation, is that as the ground motion comes up below, it gets trapped in the soil layers directly at the surface. So that white boundary is indicating the difference between the soil on top and the rock beneath. And you can see here the trapping of that waves in the soil layer, which leads to shaking which is both stronger, the colours are darker, and also shaking which lasts a lot longer than the shaking in the rock to the side of it. Okay? So this is an example just in Heathcote Valley, but I'll show you some more examples of this phenomena happening further around the Canterbury region. So let's jump straight into looking at some of these simulations of the Canterbury region. This is the first animation that I'm going to show you of our simulation, so I'll spend just a few seconds to explain all of the different simulations. Will have the same sort of layout, so hopefully by the end of the lecture you'll be relatively familiar at looking at these type of diagrams. So what we have is a description of the event that we're simulating. This is the magnitude 7.1 Darfield earthquake in 2010. We've got a time counter here, which initially is at 0. You'll see that this will increment as the earthquake's unfolding. And then we've got the different faults here shown as the black polygons, and the star represents what we call the epicenter, the place where the earthquake starts. And then finally we're going to see colour coding, which corresponds to the strength of the ground shaking, where darker colours mean stronger shaking. Okay, so let's have a look at this first video, and what we're going to see is the earthquake start here, and this is the evolution of how the ground motion was felt over the Canterbury region as a function of time. Okay, so the dark colours here are strong shaking. You can see this is the big red pulse that woke everyone up at 4:35 in the morning, just hitting Christchurch now. Okay, and then the ground motion's continuing to happen as the earthquake eventually stops occurring. There's no rupture on the fault anymore. And now the important aspect of the ground, the sedimentary soil, starts. Okay, notice how much stronger the shaking is here to the north of the fault than it is here to the south of the fault in Banks Peninsula. This is that trapping of waves caused by total internal reflection, that same phenomenon I was showing you with the light. Okay, and what you can see is as a result of that, even after 40 seconds after that rupture initially started, the ground shaking to the north of the fault in urban Christchurch is significantly stronger and lasting a lot longer than it is in other particular regions. Okay, so if we take particular snapshots of that as a function of time, we can see what the ground shaking looks like 16 seconds into the earthquake, 21, 26 and 31 seconds. And again, just highlighting some of those key aspects that we looked at before. I'm going to show you this video in slightly different costumes a few times, so I'll skip that slide. Okay, I don't want to get too bogged down in technical details in this presentation, but of course, when I show you a video which is changing with time and colour, everything must be right? Okay, so we do actually make, validations of these pretty pictures to make sure that it's not just a colourful show. And so here we've got an example of one ground motion record located at the Botanical Gardens and another record located at Littleton Port. And what we've got here on the right hand side in black is the observed ground shaking. Okay, so this was the observed ground shaking from that 4th of September earthquake, and in red was our simulated ground shaking. Okay, again, the same down the bottom for that location at Littleton. So the thing that you notice, two things immediately. The first one is clearly the simulation's not perfect. Okay, there's all sorts of things that we're missing in our models, although our models are relatively complicated, but we do actually pick up two key phenomena. The first one is the difference in the waveform, or the difference in the shape of that shape. If we look at the location here in the Christchurch Botanical Gardens, you can see that the duration of that shaking lasts a lot longer than the location in Littleton Port, where we really just have one or two large spikes of shaking. And then the other important thing is the difference in amplitude. Okay, it may not look apparent because both of these different waveforms are scaled to have the same maximum value, but this value here, the peak ground velocity, is how large the level of shaking was. And you can see at Littleton Port, it's about 24, and at the Botanical Gardens, about 53, so a factor of a little over 2 different. So while our simulations are not perfect, they do capture the most important features of the ground shaking, and therefore this is how we build confidence in those models. We can look in a lot more detail at these. Here's one example where the y-axis is a metric for how strong the shaking is for tall and flexible buildings, and the x-axis here is a function of distance. We have this very nice simple black model that we were looking at before. This was our empirical average. And then in green, we've got all the observed records, and in red, we've got all the simulated records. Okay, it looks a little bit like a mess, but the important thing is we see both a large variation in the observation, but also the simulation. Okay, so unlike that average black model, our simulation is also picking up the large variation that we see in the ground shaking for a given value of distance. And then another sort of similar figure, but now looking at a y-axis value which corresponds to more moderate to tall buildings. We see two different sort of clusters of shaking. One is those sites located on the basin edge, and other sites located further away from the basin. Okay? And when I'm talking about basin edge, I'm thinking here particularly southern Christchurch and central Christchurch, as opposed to, for example, Rangiora, Amberley, Darfield, and so on and so forth. Okay? So where you are, not just how far away from you are from the earthquake, also matters in terms of the amount of shaking you feel. Okay, these calculations are pretty intensive. If we talk about actually how much computation we're having to use, that model of the Canterbury region was 140 kilometres long, 120 kilometres in the other direction, and 50 kilometres deep. And our model for that region, hundreds of kilometres, is on a 100 metre by 100 metre grid. Okay? So collectively, that animation that I was showing you had 773 million grid points. Okay? And we solved that problem every time step at an increment of 1/200th of a second for 100 seconds, which means we do 20,000 different time steps. So you can start to see that this is some big computation. Okay? And so we use the computing resources that are available at a consortium called NESI, which stands for the National E-Science Infrastructure. One of the computing resources is the UC supercomputer, which is the one shown here, opened about 5 years ago by the Prime Minister John Key. In these particular calculations, we use about 25% of the maximum computing power of that machine, and the calculation takes about 4 hours. Okay? Relatively quick, 4 hours is not too long. You know, we can do a calculation and get some results relatively quickly. The important thing is that if we try to do it on a laptop, it would take about 100 days. Okay? So clearly, by the time we sort of get the answer, we've probably moved on to a different research topic because of a different funding agency or something like that. But of course, these computers that we have in New Zealand are not the biggest. Here's one example that I happened to visit last year in December in Austin, Texas. Like all things Texas, it's bigger, and also they name their supercomputers after some sort of Texan animal or cowboy hat or something like that. Okay? We measure the strength of the computers in terms of what we call flops or calculations per second. This one is 10,000, this one for the same unit is 20. Okay? So you can see there's quite a big difference there in terms of those aspects. These calculations, although they may seem relatively large, I'll show you some more intensive ones later. The other thing I want to emphasise, as well as this use of high-performance computing, is the importance of visualisation. Okay? Probably seeing that animation of the Darfield earthquake, you realise some things about the ground shaking that you haven't previously been able to understand because of the way that we were able to communicate it to you using visualisation. Okay, so this was a snapshot of that previous animation that we had before. Here we've got the same sort of one for the Darfield earthquake, but now rather than just talking about the strength of the shaking in terms of that colour palette, now we can differentiate between is it shaking in one direction or shaking in the other direction. Okay? And then finally we can also embed the visualisations onto things like Google Earth Maps and try and better understand things that way. Okay, all these animations are available on YouTube, so please feel free to have a look at those after the lecture, and therefore I'll try not to dwell on them too much. So this is the same simulation as before, but now with that colour scale where blue is representing shaking, let's say, to the left, and red is representing shaking to the right. Okay, and by understanding now the difference between movement in one direction and movement in another direction, you may make some quite different observations about the way in which that ground shaking is varying in both space and also varying in time. Okay, again, the same sort of trends as before, where the shaking is more pronounced as it moves through Christchurch City than it is as it moves through the Banks Peninsula region because of that phenomena of total internal reflection. Okay, and then the third one, when we embed it in a sort of isometric view and now look on Google Earth. Okay, it's exaggerated. the idea is none of these animations, it's not that one's better than the other, it's that each of them tell us a slightly different story of the same phenomena, and each of those can be particularly useful. The one thing I want to highlight here is how big the ground shaking was from that Darfield earthquake over the whole of the Canterbury region. Okay, you can see really the shaking affected everyone, and while most of us happened to be in Christchurch City at the time, the shaking directly on top of the fault was actually much, much stronger. Okay, so to contrast that, let's look at the same thing but now in terms of the February earthquake. Okay, let's skip through this slide. Again, we've got our fault here located directly under the city, and the colour is telling us the strength of the shaking. And the most important thing you notice is how much stronger the shaking is to the north relative to the shaking to the south. Okay? So this really was unlucky in the sense that not only was the fault directly under the city, but because of the city's position on top of soil rather than the rock, the shaking is much, much stronger to the north than it is to the south. And you can see the shaking lasts also a lot longer to the north than it does to the south as well. Again, the idea of looking at visualization in a slightly different way, again with this simulation embedded on Google Earth, you can see how much stronger again the shaking is to the north than it is to the south. Okay, it's completely finished if you're located at Diamond Harbour here. You're already having your next cup of tea, and Amberley, you haven't even started to feel it yet. So it's not just how far away you are from the earthquake, but where you are relative to the earthquake. Okay? And these complicated 3D geological aspects have a very important bearing on the strength of the ground shaking. Okay, this research has been undertaken over the last 4 or 5 years, and so we had quite a nice opportunity when the largest subsequent earthquake happened on the 14th of February 2016 to see how quickly we could produce one of these results and compare it with the shaking that we had. So immediately after the earthquake occurred, quickly did some reconnaissance, driving around Bexley and other suburbs to see what the impact was, and then realising that while there was damage in some areas, it wasn't a significant earthquake relative to the other 4 that I mentioned before, we proceeded to try and understand how well could we quickly perform a simulation of this event. So here's the earthquake source. It was located offshore in the ocean. And again, you're relatively familiar looking at these animations now. This is the ground shaking from that earthquake as a function of time. Same phenomena as before, where we see stronger shaking in the Canterbury Plains than we do in the Banks Peninsula area. The importance of this particular simulation is not the simulation itself, it's the time that we were able to perform the simulation so quickly after the earthquake. Okay? So the other solutions that we were calculating, it's taken us a few years to develop the capability to do these simulations, whereas this one, because we already had that capability, we can perform the calculation within 24 hours. And we've now been able to streamline the process of doing these calculations such that the only hurdle is that 4 hours that it takes us to run the calculation itself. So we can pretty much produce the results from these within 4 hours of the earthquake. The reason that's so important, obviously, is the timeliness, and one of the easiest metrics I can convey to you for how important that was, this particular somewhat boring simulation relative to the previous ones has been viewed over 20 times more than the previous animations I was showing. Okay, simply because we were able to produce it within 1 day, therefore it could be incorporated into a lot of media associated with the earthquakes, and therefore people started looking at the video. Okay, so the importance of that aspect there. Again, this is just showing a few different points in time when the earthquake happened after a few seconds, and then the subsequent period of time after that. And again, a comparison between the predictions and the observations. Okay, so let's look beyond the Canterbury earthquakes. And what I mean by beyond is, again, coming back to this idea that there are a lot of faults in the South Island region. The Canterbury earthquakes in 2010 and 2011 happened to be very close to the city, but there are many faults in the Southern Alps. And one of the most important ones close by is the Porter's Pass fault. If this earthquake breaks in the exact nature shown there from one end to the other, we expect that to be able to produce about a magnitude 7.4 earthquake. Okay? So we want to understand, using some of the methods that I've shown you already, what would we expect in Christchurch based on this earthquake happening at some point in the future. Okay, but as I sort of started to allude to before, when we're making these predictions, we want to make sure that those predictions are accurate, and so we need a way that we can actually test the quality of this prediction. The difficulty, of course, is how can we confirm how good our model works if the event hasn't happened, and the thing that we can do instead is take another earthquake that occurred relatively close by. Okay? So this little circle here is the location of an earthquake that happened on the 29th of April 2011, a few months after the February earthquake, and it was magnitude 4.9. Okay, so it's a relatively small earthquake. Pretty sure that none of you would have actually felt it. You may have seen it on GeoNet, but you didn't feel it. But we can use these smaller earthquakes to validate our computational models such that we have more confidence in their ability to predict larger earthquakes. So here's the simulation of that magnitude 4.9 earthquake. You can see it's really just a point that releases the energy, and the wave is relatively simple to start with, but then as it enters the basin, you can see this generation of basin waves as very different from those waves which are moving outside of the basin. Okay, the big difference here, make sure you check the colour scale. This is 1 centimetre per second. On those previous ones we were looking at the Darfield earthquake, the Christchurch earthquake, it was 50 or 80 centimetres per second, so that's why I mentioned you probably didn't feel this. But again, the idea is to illustrate the complicated aspects of the shaking depending on where you are and not simply as a function of how far away you are from the earthquake. Okay, we can do this using many different earthquakes that have occurred over the region. This is the slide I showed you previously in terms of different faults in the area. So hopefully you're not too surprised when I show you that the last 15 years of earthquakes in the South Island look something like this. Okay? Don't worry about what each beach fault means, just think of a different circle there as a different earthquake. You can see they're slightly different sizes. The bigger ones are bigger earthquakes, the smaller ones smaller earthquakes, and they actually do relatively well in terms of clustering with where the faults are, right? You see most of the faults are sort of in this diagonal band across the South Island, and that's actually where most of the earthquakes occur. So one of the important things is while we can't predict the location of the next earthquake, how big it's going to be and so on, we do know certain regions of the country that are more susceptible to earthquakes than others. Okay? If I take these different earthquakes that I mentioned before, we can do simulations for each of these. I'm not going to show you them all, we haven't done them all. But if I simply show you the locations of all the instruments where we can record the shaking, and then I draw a line between the earthquake and the instrument, then I get a plot that looks a little bit like this. Okay? So the red values are our earthquakes, the blue triangles are those instruments that record the shaking, and the black line between them is essentially saying what part of the earth that wave moves from the earthquake to the instrument that records it. Okay? When looking at this image, the areas with a lot of black are areas where we're essentially able to test our models particularly well. You can see that because of the Canterbury earthquakes, we've got a lot of black lines in the Canterbury Basin area, but actually in some areas, for example here in eastern Otago, we actually don't have enough earthquakes to really test our models properly. Okay? That doesn't mean we can't do predictions, but we would expect that the quality of our predictions in those regions are not going to be as good as they are in other locations where we can test them. Okay? Again, coming back to that idea of weather forecasting, weather forecasters are using the weather patterns every day, testing how good was their forecast with the observation and using that to improve the models. That's why weather forecasters can predict average weather so well, because average weather happens very often. Okay? It's the rare weather patterns that are much harder to predict, but by improving our models continuously, we're able to continuously do a better job. So there's a very strong analogy there between weather forecasting and forecasting earthquake ground shaking. Okay, so we started a little bit late, so I'm probably actually on time. In terms of the last part, which is of course the title of the lecture, what will an Alpine fault actually feel like? I hope you start to understand now that if I'd just gone straight to the slide, you would have missed a lot of the good stuff. So again, we're back to the same image as before, the South Island. We've got this long red line representing this plate boundary fault, the Alpine fault, which is splitting the island in two, not literally. And we know historically the Alpine fault has ruptured in large earthquakes in the past. Okay? We know for certain that the last rupture, major rupture, what we call an end-to-end rupture over a large part of the fault, happened in 1717. We know this primarily because of the significant number of trees that died around that time. And of course, as you know, trees grow in one ring every year, so we can make use of the growth and the stuntedness of the growth to back calculate the time of that last earthquake. We also know from other geologic studies that there's been 24 major events over the last 8,000 years. Okay? I won't go into the fine details of those, but there is a significant variation. On average, it's 310 years each time it ruptures, but it can vary from 200 years to 500 years. Okay? Earthquakes are not simple. Actually, the big ones are slightly more simple than the small ones, but we don't know when the next large alpine fault earthquake will happen. Okay? Because of that, we shouldn't be focused on that question. What we should focus on is when it happens, because it will happen, how is it going to impact us, and how can we prepare now to reduce that impact. Okay? That's what we should be focusing on. So that's the idea behind the work that we're doing, is that while we don't know the exact nature of the earthquake, we can learn about the ground shaking that that earthquake might produce. Okay? So the simulation that I'm going to show you here for the Alpine fault is not the Alpine fault. Okay? It's one possibility for what the Alpine fault may rupture, and it's what we call a rupture that involves the southern part of the Alpine fault and the central part of the Alpine fault. Okay? It stops here around Arthur's Pass, a region where the location of the fault becomes quite complicated, and we have some reason to believe that that may be the upper point where the rupture happens. Okay? But it is possible that the rupture could continue. It's possible that it could start here and finish just here, and we'd get a magnitude 7.5 earthquake. Okay? So the solution that I'm going to show you isn't the definitive answer for what will happen. It's one possibility. But of course, we can simulate those many possibilities and understand for each different possible future earthquake what the consequences might be. Before I do that, however, let's just get a sense of scale. Okay, so let's look at the size of the fault. This is one of our representations of the ground that moved in the magnitude 6.2 earthquake on the 22nd of February 2011. Okay, as you can see from the two different horizontal and vertical scales, the fault was about 16 kilometres long and it was about 9 kilometres deep. Okay? It started around about here, and then each of these different black parts represent contours, the time that the earthquake was actually breaking. And this is what the Alpine fault looks like under that one scenario that I was showing you before, what we call the southern and central segments. If those two segments rupture together, it will produce approximately a magnitude 7.9 earthquake. The important thing to understand here is we're talking 410 kilometres long. Okay? So if we actually move that 22nd of February earthquake to scale, it looks something like this. Okay? The other thing to note is that the maximum movement on that fault is somewhere around 200 centimetres or 2 metres for that magnitude 6.2, whereas we expect that the maximum movement on the Alpine fault may be on the order of 10 metres, 11 metres or so. Okay, so we're really talking about something fundamentally different. We're going to have about 350 times the amount of energy released from that earthquake than we have from the magnitude 6.2. If we think of the analogy that I tried to capture your attention on before, between the 22nd of February earthquake, 6.2 in magnitude, and the Darfield earthquake, 7.1 in magnitude, the main difference was not how strong the shaking was right beside the earthquake, but how wide or how far in distance the shaking was important for. Okay, so the animation that I'm about to show you is indicating that an earthquake that large is going to produce ground shaking over the entire South Island rather than at one point. Okay, so the image that we're going to see is a video that looks something like this. I'm only going to show it once or maybe twice if people choose to request it. Just a few details to kind of keep you in suspense. From a computational perspective, we've got about 25 billion points that we're solving this model for, over 50,000 different points in time, and it uses about 80 times the amount of computation of those previous calculations, which were just focused on the Canterbury region. Okay, so we quickly start to run into the point where we can no longer do some of these calculations. We use the full capacity of the supercomputer here at the University of Canterbury for 4 full days. Okay, so about 1/100th of a year, our single calculation stopped everyone else from doing their research. About 30 years for us to do on a single laptop. Okay, again, so just highlighting the importance of these calculations. The other thing, of course, some of you may be thinking, well, computers are getting faster all the time, it's no problem. what inevitably we find in the research world, and this is not just in earthquake engineering but any discipline, is as our computational ability increases, as computers get faster and faster, so does our aspirations. Okay? So in 5 years from now, we're wanting to do a calculation that instead of on a 100 metre grid, it's on a 5 metre grid. Okay? So this problem of pushing the boundaries or being on the bleeding edge of this computation is always going to be an issue that we're always striving to push. Okay, so let's have a look at the calculation. We're moving really fast in time here because this is going to take a while. Here's the rupture starting initially down in Fjordland and moving up the fault, okay, from south to north. It's taking a long time because this is 410 kilometres long. We're already 50 seconds into the shaking. People in Christchurch have absolutely no idea what's going on. But Haast has already felt the full impact of the earthquake. Okay? The ground shaking continues as it ruptures up the fault, moving at the speed about 4 kilometres a second. And the important thing from one perspective is to understand what happens as these waves enter the Canterbury Basin. Okay? This is total internal reflection happening, where that ground shaking is getting trapped inside the soft sediments in Canterbury, and as a result of that is causing shaking which is both stronger and lasts a lot longer than in the rock around it. Okay? It's not going to produce shaking as strong as that in the 22nd of February earthquake, but we're already at 3 minutes and the shaking's still going. We've finally hit the full South Island where we've hit Nelson, and the shaking's still happening in Canterbury, and it's also still happening over here on the west coast. Okay, so we're now at almost 4 minutes from the time that the earthquake started, and we're still getting a little bit of movement here in the Canterbury Basin, although the amplitude of that movement's quite small. Okay? So to reiterate that idea again, that the ground shaking is very different than what we had during that 22nd of February earthquake. And most of you, by the time you really realised what was happening, the earthquake had actually, or the ground shaking from the earthquake had already stopped. It was really 10 seconds of very, very intense shaking. In this case, we get a much longer duration ground motion. Sometimes you'll refer to it as a sort of a rolling motion. That doesn't mean that it's very low in amplitude, but the main thing is that difference in duration. And that's literally caused by the fact that it takes about 150 seconds for the whole fault to break. Remembering it breaks first at one point and then moves slowly to the north as a function of time. Okay, so what should we do about this? Well, as I mentioned before, we can't predict when the earthquake is going to happen. All we can do is better understand what the implications might be. From a quantitative perspective, it's really important that we're able to understand where the shaking is going to be stronger than where it's going to be weaker, because in a world of limited resources, we've got to be able to justify why we need to do something in some location versus some other particular location. If we're very vague about, well, it may just be bad, let's just put it in the too hard basket and do nothing, we're in a much worse situation than if we can make use of some research, in this particular case, to advance the way that we do things and collectively become a lot more resilient. The main thing that I want to highlight that's different about a large magnitude earthquake, and again, like I said, it's not just the Alpine fault, there are many earthquakes throughout New Zealand, throughout the North Island as well as the South Island. The importance of the Alpine fault is that you all know it, and so it's very good for us to have a dialogue about what may happen, why it's important, and what we can do to try and improve things. When we have large magnitude events, one of the important things to think about here in Canterbury is that we are not the only ones that will be affected. Okay? In the Christchurch earthquakes, it was all on us. Okay? There was a lot of damage, but everyone else was coming to the rescue. In this particular case, the whole South Island will feel the impacts of this earthquake, and we may not be the first ones that get help. Okay, so we should expect to have to be a lot more independent, even though the particular damage to the Canterbury region may not be as severe as from the February earthquake. And the areas where New Zealand's most vulnerable is what we call the lifelines. Okay? The word lifelines is very intentional. They are the things that without we cannot live, and they are things like state highways, railways, the national power grid, and other, for example, underground pipe networks and so on. Okay, many of us have realised we never thought about the water network and the sewer network before the Canterbury earthquakes, but after those earthquakes we realised, one, how vulnerable they are, and two, actually how important they are for us living the way we do every day. Okay, it's the same thing. We know, for example, statistics like if we don't start stocking up a supermarket, it'll be empty in 4 days. Okay, one of the most important things, for example, from the magnitude 9 earthquake in Japan was not the damage in large cities like Tokyo, but was actually the disruption to the supply networks that resulted in lack of food, lack of resources in Tokyo City itself. So these lifelines are the areas where New Zealand is both most vulnerable but also most reliant. And one of those which deserves particular attention is our 3 Alpine passes. The first one here, Lewis Pass, the next one here, Arthur's Pass, and the third one here, Haas Pass. You can imagine that with the strength of the shaking that I was showing you on the previous video, which was the strongest immediately beside the fault, you can expect a lot of landslides in those areas. Okay? And we've seen, for example, last year's winter, one relatively decent amount of rain over the Arthur's Pass area caused a single landslide which blocked the road for several days. Okay? One isolated landslide when everything else in the region was perfectly fine and everyone could, all the contracting crews could get there and help, still took about a week to actually clear the landslide and open the road up again. So hopefully you won't be too surprised when I tell you that based on doing things the way we do, the New Zealand Transport Agency expects that some of those Alpine passes may be closed for at least 6 months. Okay? And of course, these are the only 3 ways by land to get from the west coast to the east coast. So think about the impact that starts to have on tourism, starts to have on our commercial sectors, and general way of life. Okay? So the title of my talk was what will the Alpine fault feel like, not what will the impacts be. So I've given you kind of a quick summary on some qualitative aspect of the impacts, but a more detailed treatment would be reserved for another discussion. So lastly, I want to thank a few people. This is kind of at the end of the technical aspect of my presentation. The first thing is that I'm up here getting the benefits of talking to all of you, but there's a huge team working beside me, not behind me, beside me, doing all of this research. Okay? And these are all the people that have directly been involved in the quantitative research itself, not just people sort of helping me on the side, but people really involved in the process. You can see these are a lot of students. Obviously here at the university we have a key goal to develop new capabilities and leaders of the future, but we also have people from completely different disciplinary backgrounds. We've got engineers working with geologists, working with a bunch of people from overseas, and a huge amount of computational people, given how intensive these calculations are, both to do the calculations and then also to create the visualization as well. So I'd just like to take the chance and get you all to thank these people, many of them are in the room, so just a quick round of applause for them. And then as well as this being a key area of research that I do on a daily basis, I'm part of a much greater network, which is what we call Quake Core, where the word core stands for Centre of Research Excellence. It's one of the 10 government-funded centres of research excellence in New Zealand, funded at $20 million over 5 years. We have 8 key partners across New Zealand from different universities and Crown Research Institutes. And across the work that we do in Quake Core, we're really tackling some of these hardest problems, such as the ground shaking caused by Alpine faults, the impacts of liquefactions on infrastructure, what we do about heritage buildings in terms of their safety, economics, and resilience. How do we develop new buildings in the future which won't actually be significantly damaged by earthquakes? And how do we understand the important social aspects associated with earthquakes as well? Finally, a quick announcement to the funders, and thank you very much for your time.